Let me share. Okay, so yesterday we were discussing about one uh, another aspect of interference where uh, we learned that you can also obtain an interference pattern by dividing the amplitude of an incident wave. So if we take a thin film medium with certain thickness d, let's say, and doesn't matter whether the incident wave it's a normal incident or it's a oblique incidence. So in any case, so there is a possibility that because you have now two interfaces, so this is your interface one, so this is your medium one, this is medium two, and this is your medium three. So here refractive index is n1, here n2, and here the refractive index is n3. So uh, if you have such a medium, so if you have two different interfaces, so interface 1 and interface 2 here, so this is the second interface. Uh, the light, it can get reflected from the top surface, so there will be a reflection here, and there is also a reflection that can happen from the bottom surface, let's say like this, and these two red and black ones, so they will interfere. They can interfere constructively or destructively as well, and you will obtain a fringe pattern very similar to the interference pattern that you observed in case of a double slit experiment. Now, the condition for interference is changes a little bit because normally we say if the path, so the optical path difference here that is traveled by the black ray is 2n. So if we are taking the medium 2, which this is the film or the thin film that has the refractive index n2, so it is 2n2 into the thickness d. And now the condition for maxima and minima will be reversed because on one interface or one surface, the top surface, when there is a reflection, so there is a phase change in uh, the wave has a phase change, and that gives rise to an additional path difference between your two reflected beams. And this additional path, this phase change is by pi, and that corresponds to a path difference lambda by 2. And that's why the condition for maxima and minima will be different. So now you have to account for this extra path difference lambda by 2 introduced due to the phase change. And so this is will be now your maxima, and minima will be when your path difference is equal to m lambda, and m is your 0, 1, 2. So these are integers. So towards the end, so I gave you three situations. So three different thin film possibilities. So the one possibility was, so we have this is glass, both are glass, and we have a thin film of air. Now, the second possibility is we have glass and then we have oil. So this is a thin film of oil. Now you have another possibility. This is, it may be a glass. This is, let's say, oil film, and this is a flint glass where the refractive index is much higher. So refractive index I will write here, the 1.5. So air we assume is 1. This is 1.5. So here refractive index 1.5, 1.5. This is about 1.6, the oil film. Then this is 1.5, this is 1.6, and this is about 1.66. So we have three situations, and the question was what will happen to this condition. So all are like, we have a thin film here. So one is air film, one is oil film, and the other is oil film, but now sandwiched between a refractive index of materials where, so the upper one is, so there is a grading or graded refractive index for the film. So that means when you are looking at it, so refractive index is basically increasing in this direction. So what would happen to this condition for interference for these films? So any answer you have? So in the first case, air film, so there is no change in this condition. So it will remain the same. Why? Because from the top surface, this interface, glass and air, the first surface, this one here. So, oh, sorry. So if you have this surface here, so you have this is, light is coming from a denser to a rarer medium. So there will be no phase change, but there will be a phase change. So let me draw that. So the reflected, I'm just plotting the reflected one. So this is the reflected one from this interface, and this is the reflected one from this interface. So now the red one, there is no phase change, but for the black one, there will be a phase change because it is going from a rarer to a denser medium. And that's why this situation looks very similar to the one we just described, and therefore the condition will remain the same. So that means, so this delta path difference m lambda, when it is the path difference is m lambda, that is your medium. So in the second case, so I have, let's say again, this red one and a reflected one. This is the black one. Okay. So from the red one will undergo a phase change because it is oil film has a higher refractive index. So that is, it is coming from a rarer to a denser medium. But the black one, for black one, there is no phase change. So again, the situation is very similar to the one we just saw. So in that case, the condition will again remain the same. So m plus half lambda will be maximum. But in the third case, the situation is different. Now, when the red one here, so there is, sorry, so there is a phase change for the red one as well as for the black one, which is reflected from the lower interface. Because now I have put a flint glass where the refractive index is much higher than the oil film, and therefore both waves are basically undergoing a phase change by pi, or an additional path difference introduced lambda by 2 by both the waves. So therefore the addition will be again a path difference of lambda, which will exactly, we will have a situation where it looks like for the condition for the Young's double slit experiment. So in this case, delta will be m plus half lambda, that will give rise to a minimum, or delta is equal to m lambda will be a maxima. So the situation changes in the third case, because we have both the waves are undergoing a phase change due to reflection. So this is a very general condition that we can write down in the case for the third case. So we can write down that if I have a situation where I have a medium 3 medium, so where Ni is less than N2 less than N3. So in that case, the condition of maxima and on the interference condition would be so delta is equal to m lambda. So that will give rise to a maxima, and this is m plus half lambda will give rise to a minima. And we are assuming that the incident wave is it is from the top side. So this is, let me draw that. So we call this one as the light is incident in this direction. This is N1, this is N3, and this is N. So if you have such a graded refractive index, so you would expect that this is the interference condition, which is different from like a thin film that we observe. So this has it has tremendous application, and we will look at some of those applications. And today also what I want to show you that I mean, we haven't used really the electromagnetic wave and understood how this optical phenomenon work. So I will give a simple, so it is a little bit rigorous in mathematics, but I want to show that because you will appreciate that how electromagnetic wave, this Maxwell's equation, can be used actually, or actually it was the Maxwell's equation that led to this kind of application that I am describing right now. So let me first describe this application, which is the design of anti-reflection coating. So it is a design of anti-reflection coating. So what it means, so if I have a glass medium, let's say, okay, and I have an incident wave, so there will be always some amount that will be reflected back. Now, what is done in this technology? So what is done, so if I have any surface, so that doesn't matter, it is glass, it can be any surface, I can put another material, another coating on top of it, okay, and so this coating, this thin film, will have certain thickness d, and the refractive index is, let's say, nf of the film. So this is, you can say, ng, let's say, and this is your air na refractive index. So what this coating, you want to put this coating on so that you reduce the reflection or the light that is reflected from the surface. So you want that most of the light, it should get transmitted. So what goes on inside is not the matter, but what is aimed is to reduce this reflection. And this is what this anti-reflection coating would do. So that means we have two things to optimize here for the coating. So one is, so the D, that is thickness, and the refractive index. Both needs to be optimized so that your wave, so if you are saying the incident wave has a wavelength lambda, so this lambda will not get reflected, rather it will get transmitted through the material. So I will first show you a qualitative explanation, and then we will go to the more rigorous part. So a general way to understand, or is very in a to understand it in a qualitative way. So let's assume. So I think you are already aware of this. So if I have a surface, let's say like this. So this what I'm saying, one can also obtain using or derive it from Maxwell's equation. So we have N1 and N2, two different medium. So if I have incident light with amplitude A, so the reflection would be R into A, and the transmitted part is T into A. So R and T, what is R? R is equal to the reflected reflection coefficient, which is your N1 minus N2 by N1 plus N2. Okay, so this is the reflection coefficient related to your refractive index. Your transmission coefficient will be so this one can actually derive from Maxwell's equation, and we will show that for a general in a very general manner. So then you can apply it for specific cases. So T is 2N1 by N1 plus N2. So this is how the reflection or you can calculate, if you know the refractive index, so you can calculate what is the amplitude that is reflected and what is the amplitude that is transmitted. So if I take a glass, so if N is equal to 1, so this is the situation, let's say. So this is my glass and this is air. So in that case, N1 is equal to 1, N2 is equal to 1.5, and your reflection would be, so if you calculate, that comes out to be about the intensity that is reflected. So this comes out to be 0.02, and the intensity will be the amplitude square, will be proportional to R square, which is almost like your 4% of the incident wave will be reflected. So this is just when you look at the air and glass interface. So 4% of your wave will be reflected back, which is not good when we talk about some applications like telescope, for example. So when you are using a lens, and because you are looking at the sky, and the amount of light that is coming in is really, the intensity is small. So you want that all the light should be transmitted, so there should not be any reflection. And on top of that, in a telescope, you use not only one lens, so there are several lenses. So it's a set of lenses, and for each lens, there will be a reflection. And so that means the loss due to reflection can be very high, which you don't want. And that's why many of these lenses are coated with a anti-reflection coating to minimize this reflection. So, yes.
Sir, how we got R is equal to 0.02?
Oh, that we substituted here. No, so we know N1 and N2. So it is R will be equal. So we know what is N1 and N2. So it is. So here we are saying it is 1.5 minus 1 divided by 1.5 plus 1. So intensity will be this amplitude square R square. So this is so if you calculate this, which is what the number you will get this much. Okay. So this is from this is the number you can calculate.
So it would be 0.2.
Let me see. So R will be, so this is R is
0.2.
0.5, 2.5. So it will be
Yes.
0.2. Okay, yeah, that's right. So it will be 0.2. Yeah, that's why you have. So it will be 0.2. So it is. Yeah, so this is 0.2. So that will lead to a yes, I mean, it can be 0.2 or minus 0.2, but normally when we are calculating intensity, so we take the square of that. So that's why it will be like a positive, say always a positive term. So if R is equal to 0.2, that means about
4%.
4% would be reflected. Yes. Okay, so now we want to actually look at what is the condition for this. So now, how do we reduce this reflection? Okay, so this 4%, if you want to reduce, so how would you do that? So in that case, what we need to do is make sure or take a thickness of the coating. So what we are doing now is we have, let's say, a glass surface, and now I put a coating with thickness D, and what I want that when there is a reflection, so one reflection will be from this bottom one and one reflection from the top surface. So now I want the thickness is such that these two beams, these two waves, they will interfere destructively. So if that is the case, so then I can reduce the reflection, because now the beams, the waves that come out, they will interfere destructively. So I will not see any reflection, and most of that will be transmitted then. So I would choose a material for a coating which has, let's say, when we say this is the refractive index of the film, so I would expect that the path difference 2NF into D should be equal to M plus lambda n plus half lambda. So that is what we saw the condition for uh, destructive interference. So here we have air. This is n is equal to 1. This is nf, and let's say this is n is equal to 1.5. So I should have a material with nf such that n should be less than nf, would be ng. Okay, so this should be the one condition. So the refractive index of the material should lie in between that of your glass and air, and also this condition will tell me what should be the value of d. So the thinnest one I can have is, so m is equal to 0. So in that case, the thickness I would expect is 4 nf. So if I deposit a film or a coating on glass surface with d equal to lambda by 4 nf, and where nf should lie, the refractive index should lie between that of air and glass, so I can create a condition where I will only have a destructive interference of the reflected wave, and then I can minimize the reflection. Okay, so this is the idea behind this anti-reflection coating. So we will now, I just give you one material. So this is MgF2 magnesium fluoride, which has a refractive index about 1.38. That is typically actually used for this anti-reflection coating. So you have also this anti-reflection coating on your eyeglasses, for example. So now let's look at this, how we can obtain this condition from solving the Maxwell's equation. Okay, so this is I want to show that here we will be using some mathematics here. I will also skip some of the steps as well. So what I would suggest that you can also look it up in the book in the relevant section, and then you will understand the mathematics. So it is a little bit you have to do on the pen and paper, so then you can understand it. Okay, because so maybe listening to me will not help. So if you write it, you will understand it better. So let's start with our Maxwell's equation. In a dielectric medium. So we have, because we are talking about glass and so on, so it is a dielectric. So let's start with this. So we have the Maxwell equation, del dot B is equal to rho. Then your del dot B will be equal to 0. Then del cross E will be equal to minus del B by del T, and curl of H we will write as J plus del D by del T. And what is your D? D is your electric displacement vector, which is related to your electric field by this relation. And B is your magnetic induction, which is related to your magnetic field mu H. And your J is current density, which is related to your electric field in this relation, sigma E. Okay, so this is your Ohm's law, basically, the last one. So if I assume what is epsilon mu, epsilon is the permittivity of the material, mu is the permeability of the material, and sigma is the conductivity. So now if I assume there is no charge in the medium, so I can say rho is equal to 0. So let's say charge free dielectric. So in that case, the equation I can write down, and also I can assume that I don't have any conductivity because it is a dielectric medium, so no charge current is there. So I can assume J is equal to 0 as well. So in that case, the Maxwell's equation become even simpler. Then I say del dot H is also equal to 0. So both B and H, they are divergenceless. Curl of E will be equal to minus mu del H by del T, and curl of H will be equal to epsilon del E by del T. So it becomes a little simpler. And what is the possible solution of E and H? So you can write E and H, the possible solution would be like plane wave, where you can write E is equal to exponential I k dot r minus omega t. So this is your E vector, and the H would be your H0 exponential I k dot r minus omega t. So now you use these are the plane wave solutions. So now if you calculate the first two terms, del dot E equal to 0, I think you have done that already, so I'll not go through that. So you can then find out E, I mean E and H, your electric field and H vector, they are perpendicular to your K vector propagation direction. So K dot E will be 0 and K dot H will be 0. So that tells you E and H are perpendicular to each other. And you can also substitute these solutions in the third and fourth. So curl of E, so you can calculate curl of E and curl of H, and till or from that you can say that so if you do that, so you will get a relation between such kind of relation. So omega mu and E will be equal to H cross K by omega epsilon. So this so the first two, you this K dot E equal to 0, K dot H equal to 0, when you do calculate the first or solve the first two Maxwell's equation, these two, and the second two you will get from this. Okay, so the first one tells you that your electric field and magnetic field, they are always perpendicular to your propagation direction, and these two tell you that all K, E, and H, all the vectors are perpendicular to each other, and that is what shows you the transverse nature of the electromagnetic wave. Okay, so there is also a relation between E and H. So we can calculate the amplitude of electric field if we know the amplitude of magnetic field, and vice versa. And what is the relation? So the relation H0 is equal to K by omega mu. So you obtain it while solving this Maxwell's equation. I think you have done that exercise many times. So this is what you will get. And if you multiply that, so these two equations, so you will get a relation which is K will be equal to omega epsilon mu, or you will calculate then the velocity of the electromagnetic wave, which is nothing but this is the velocity of the electromagnetic wave will be epsilon 1 square root of epsilon mu. So in free space, this is nothing but velocity of light. So this relation one can write in a slightly different way. So we can write this relation. So I am going through this quickly because you already know it. So K cap E, so we can write it down as K by omega mu into K cap cross E which in optics sometimes it is written as in this form, k cap cross E. And what is, so this is a relation which probably we will come back to this relation many times. So what is eta? Eta is nothing but omega mu by k, which is if you substitute the values of this k, and so in terms of epsilon and mu, you can write it something like mu by square root of that. So if you substitute those relation, k is equal to omega. So this term is known as intrinsic impedance. This is intrinsic impedance of material. Why it is impedance? Because if you look at the dimension, the dimension of eta would be dimension of E by dimension of H, which the unit would come into omega. Okay, so that's why this is known as intrinsic impedance. And for a dielectric material, so if I take a dielectric material, this mu you can actually approximate by mu naught for most of the dielectric material. The the permeability doesn't change so much. So in that case, your eta compared to your free space impedance. So let's say if I say this is free space, so we have the free space will be mu naught by, so this is mu by epsilon divided by mu naught by epsilon naught. Now for a dielectric, say we say mu is equal to mu naught, so in that case it will be equal to epsilon naught by epsilon, which is nothing but your 1 by n. So this is your, n is your refractive index. So your impedance, the material to the free space, is inverse of your refractive index. So in that case, we can we have a relation between E, the amplitude H naught, and E naught, or where we say H is 1 by eta into E. Okay, so we can just simply write in that case the amplitude will be of your magnetic field. If you know what is the electric field, so you can calculate your magnetic field amplitude just by this relation. Okay, so from this expression, you can also calculate the wave equations. The wave equation that we wrote in the beginning. So you can write del square E would be equal to epsilon mu del square E by del T square, and also del square H will be equal to epsilon mu del square H by del T square. So that means electric field and your magnetic field H both are propagating very similar to your like a wave. And here when we say it is a wave, so what is oscillating is your electric field and the magnetic field. And also, so there are many other properties of electromagnetic waves, so we'll not go into that. What I want to just this brief introduction, and then we directly go to a very generic problem, and we will see how that can be used for calculating the or how that is useful for calculating the reflection coefficient, and eventually how we can use that to for this anti-reflection coating. Okay, so this is a very general situation we have. Let's say again, let's go to this here. So I have, this is the situation. So let's say I assume that this is my x equal to 0 and x is equal to d. So this is I define my coordinate system like this. So this is my x-axis, this is my z-axis, and the outer plane is my y-axis. So the electric field, I assume, is oscillating along the y-axis, and magnetic field is along z-axis, and the propagation direction is along the x-axis. Okay, so let's assume that. So this is the incident electric field. Okay, so we are not assuming any refractive index or anything. So just simply by solving the Maxwell's equation, we will actually go to those relation that we found out for reflection and transmission coefficient. So you can do it for a one simple medium, uh, just taking, so removing the second part or the second surface, say. But let me do it for both the surfaces, because for the completeness. So there is one incident wave E1 plus, we call it, and then the electric field that is reflected back, so we will call E1 minus. So similarly in this medium, so there will be an electric field that is E2 plus, then there will be a reflection from this, that is E2 minus, and then eventually there will be an electric field that will be transmitted, E3 plus. So this is your medium 3, this is medium 2, sorry, this is medium 2, this is medium 1. So your light is, we are now, it's coming from this side. So this is the positive x direction, this is positive x. So now x is 0 at this surface, x is equal to d this surface. So the thickness is d. So you can write down the electric field. So anyone can tell what should be the electric field? How should I write down? So if I am assuming that the electric field is along y direction, so I can write this y cap E10 plus, so in the medium 1, so this is medium 1, I can write down it as exponential I k1x minus omega t plus y cap E10 minus exponential minus I k1x plus omega t. So remember, so why I'm doing that? Because so this represents the incoming wave or incident. This is your reflected. So that's why this minus I comes here. Okay. So you can write these for all the three mediums exactly the same way. So for the second case, I will write it E20 plus exponential I k2x minus omega t plus y cap E20 minus, again there's a minus sign here, k2x plus omega t. So k1, k2 are basically your magnitude of the propagation vector. So it will depend on the wavelength, what is wavelength in that medium. So E3 we will write as y cap E30 plus exponential I k3x. So you will see in when we do this mathematics, we introduce a small a phase factor I k3d here, which actually simplifies some of the problems when you do solve the mathematics. So that's why this part is introduced here. Otherwise, normally you should write it I k3x minus omega t. But this is this exponential I k3d is a, or rather it should be k2d actually. So k2d is a phase factor. For some simplification of the while solving this equation. So we can then write the corresponding H fields. So which we know k, this is k cap cross E. So using this expression, we can write what is the H1, H2, and H3. So I will, so remember when, so write those expressions down. So if you know this using this relation, and then what needs to be done is, so quickly let me do that. So you will write then what is H1, what is H2, and what is H3. Okay. So now what we do is we do apply the continuity equation. So apply the continuity equation at the at x equal to 0 and x equal to d. So if you do that, so you will get a expression. It is very simple. So because these are all tangential component, so we will say the tangential component will be all continuous for both electric field and the magnetic field, because it is a dielectric medium. So for a conducting medium, the continuity equation is different. So since it is a dielectric medium, so the both electric field and the magnetic field will be continuous at the surface or the interface. And if you apply that, so you will get a relation, uh, something like this. So I will write down the final one, E10 plus and E10 minus will be equal to, so here you have this eta 1 and eta, so you will have this eta, so for each medium, so you will have eta 1, eta 2, and eta 3. So that is different. And what is eta? Eta would be equal to your, will be proportional to 1 by n, the refractive index of the material. So that means when you take uh, the ratios, so you will see this, it is nothing but equal to your refractive index of the material. So E10, and so you can write it down in this simplified version. So after writing and applying the continuity equation, so you can write it in this form. 2n2 n1 minus n2 by 2n1, n1 plus n2 by 2n1. This is E20 plus and E20 minus. Okay. So similarly, you will also have an expression for E20 plus and E20 minus with n3 by 2n2 exponential minus ik2d. So let me just quickly write it down. E3 plus. Okay, so this is one relation between the medium 1 and medium 2. This is the relation between medium 2 and medium 3. And if you combine these equations, these two equations, so you can find, so then in place of E20 plus and E20 minus, so you can substitute this here. And if you do that, so you'll get a big expression where you can write what is E10 plus and E10 minus. So I will not write that because it will be simple. You can just put it there and calculate that. But you should do that on your when you solve it. And to calculate the reflection coefficient, so R, which is your reflection coefficient, is equal to E10 minus by E10 plus. So after you substitute that, so you will calculate the expression for E10 and E10 plus and E10 minus, so for the incident and for the reflected one. And if you take the ratio, so you'll get the reflection coefficient, which will have this form: ik2d plus r2 ik2d exponential ik2d plus R1 R2 exponential I k to d. And what is R1 and R2? R1 will be N1 minus N2 divided by N1 plus N2, and R2 will be N2 minus N3 divided by N2 plus N3. So this is the reflection coefficient, the interface, the first boundary, and this is reflection coefficient at the second boundary. And the total reflectance would be modulus of R square. And if you do that, this modulus of R square, so you'll get an expression R1 square plus R2 square plus 2R1 R2. So you will also only have the real part of the, this is the complex one, but you will only have the real part because you are taking the square. So this is 2R1 R2 cosine 2 k2d. So the purpose of doing this exercise in the class is to show you that using the Maxwell's, starting with the Maxwell's equation and writing those Maxwell's equation in different medium, and then applying the, sometimes you apply the continuity equation, sometimes you apply the boundary conditions, so you can actually obtain a solution, or you can calculate this reflectivity and reflection coefficient and transmittivity and transmission coefficient and so on. Then how this is applied to this anti-reflection coating, that is the most interesting part. So after doing this rigorous mathematics, so we will focus on this relation here. What we want, that we have a medium and we want to make it make a anti-reflective coating on it, okay, and we want to find out what should be the thickness d and what should be the refractive index n. So this situation what we just derived, so we have three or two boundaries here. So one boundary is the top one, air and the film, and then the film and the glass or film and the material. So we can write down here R1 . So R1 is equal to your NA. So this is your NA. This is, let's say, your NG. So it will be NA minus NF by NA plus NF. So R2 will be equal to NF minus NG by NF plus NG. And this K2D, so you can write down this K2D will be equal to, we can write as a phase factor delta, so which is nothing but, so when you look at it, so 2 pi by lambda into your optical path length NFD. This is your phase that we introduced, the extra one. So this is, you can write as delta. So in that case, your reflectivity would be R1 square plus R2 square plus 2R1 R2 cosine 2 delta divided by 1 plus R1 square R2 square plus 2R1 R2 cosine of 2 delta. So now our aim is to minimize this reflectance. So to minimize, so because we have to minimize that, so with respect to that should be equal to 0, okay, and then you calculate what is the condition at which this your dr by d delta would be equal to 0, and you will find that when cosine of 2 delta is equal to -1, so this is the condition for your minima. So that means your delta should be pi by 2. So for delta pi by 2, you have this condition. And what is delta pi by 2 means? So it can be delta pi by 2 is or you can write delta will be equal to, so very generic expression, so you can write as 2n plus 1 pi. Okay, sorry, this is 2 delta to be 2n plus 1 pi, where n is equal to 0, 1, 2, and so. And so if you substitute that and you can calculate in so for this glass IR and the film case, so R is, what is R? R is equal to for the minimum condition, when the condition is minimum, this is minus cos 2 delta is minus 1. So if you substitute that, so you will get R will be equal to R1 minus R2 by 1 plus R1 R2 whole square. Now we know what is R1 and R2, and if you substitute that, so you will get an expression for NA and G minus NF square the whole square, and divided by NaNg plus NF square whole square. And this condition leads to, so R is equal to 0 means, so this is should be equal to 0. That means your NF should be equal to Na and G. So you choose a material where the refractive index of that material should be square root of Na into Ng. So if I take Na is equal to 1 into Ng is 1.5, I will have a value something around 1.225. Okay, so this is the ideal material you should use for the anti-reflection coating. And the D, anyway, the condition for the D we will get from this relation 2 delta, where we say 2 delta is basically 4 pi by lambda into NFD, and D would be equal to then lambda by 4 NF. This is the one we just qualitatively saw, so it can be, these values are also possible. And so on. So all odd multiple of lambda by 4 NF. So this is how one can actually use the Maxwell's equation to obtain, find out the reflection coefficient, and then find out what is the condition if you want to have a reflectivity 0, or you want to make an anti-reflection coating. So I want to give another example to appreciate that, how this mathematical, solving these mathematical equations actually help in designing anti-reflection coating. So you know about these aircrafts, these fighter jets, okay, and normally how their presence is detected by radar, okay. So radar has a frequency in the range of 10 to, let's say, 40 gigahertz. So there is a big variation, but typically this is the frequency range, which corresponds to lambda of the order of a few centimeter, 1 centimeter or less, about a centimeter. So these waves are basically when you incident on aircraft, so they get reflected, and then you can detect that the presence of the fighter jets. But then what is actually then people do is use anti-reflection coating on the surfaces. And remember, this aircraft carrier, so if you look at the body, it most likely will be a conducting material, and therefore the reflectivity will be really high. So to minimize that, you need to put a anti-reflection coating on top of that. And so there you need to then solve these equation for the microwave. So this is basically in the microwave reason. So in the electromagnetic spectrum. So you have to solve this Maxwell's equation for the microwave range, and then you can obtain what is the optimum thickness D and what is the refractive index N. So you can optimize that. So there is a lot of research has been going on, and to choose the proper material which can be used as a anti-reflection coating on this aircraft material, that is also a big research. Still it is going on. So people have found out many ways, but still there are a lot of scopes in those areas. Yeah, so any question? So these mathematical things, what we did is again in the book from Ghatak. So you will see that you can easily see those sections in the Ghatak book, and I hope you would appreciate that with electromagnetic equations, so solving electromagnetic equation actually leads to really a lot of engineering application. So here we saw that how you can reduce the reflection from a surface by optimizing the thickness and the refractive index of the material. So when you are optimizing the refractive index, you actually are optimizing the permittivity, dielectric permittivity of the material. Okay, because your refractive index is related to your epsilon. So when you are optimizing that, so basically you have to optimize what is epsilon corresponding to that frequency range. So in the microwave range, for example. So this is one extreme. So another extreme is you can actually increase the reflection as well. So if you use the exactly opposite, the D, you can increase D by not lambda by 4NF, but another, if you give another additional lambda by 2, so you can create a constructive interference. Okay, so that will also sometimes you use in some applications where you want to increase the reflection from a surface. So both extremes actually work using this concept. So we will see maybe a couple of examples, and yeah, then move forward. Yeah. Any question?
Sir, the green color in our eyeglasses is due to this reflective coating, anti-reflective coating.
Yes, yes. Eyeglasses, you also have this anti-reflection coating. Yes. So eyeglasses, telescopes, I mean these aircraft carriers. Yeah, so these are some of the examples where, or even like when you use the photovoltaic cells, your solar cells. So there you have a glass on the top to protect the underneath your device. Now
सर
this, yes.
सर वो एयरक्राफ्ट में एंटी रिफ्लेक्टिंग कोट क्यों लगाते हो समझ में नहीं आया.
Okay. So let's say if you have so normally जब तुम्हारा aircraft जब so when it is going into the enemy's region, okay, so that sky, so they have this radar, so which actually will detect the presence of these aircraft. तो वो कैसे डिटेक्ट करते हैं? तो बेसिकली एक radar wave, so there will be an incident radar wave, and if it is reflected back, so you will have the detector which will detect it, and then they will say, oh, okay. So normally if it is a free the sky, there is nothing, so there will be no reflection of wave, so it will just go away. But if there is a reflection, so that means they are sure that there is a presence of aircraft, and so they can also detect in which direction and what is the speed and so on. That also can be detected. So that's why. So this is known as a stealth technology. So what you want is you want to make sure that your aircraft goes into the enemy sky without they cannot detect it. And how will you do that? So you have to reduce the reflection. This radar you want that the radar, whatever is energy falling on the aircraft, it should be absorbed, so it should not be reflected at all. So that's why you want to put a anti-reflection coating, so that when whatever the radar wave is falling, it gets absorbed, and or in a way you say it's a destructively interfere after reflection. Yes, there are many aspects to stealth technology. So no, this is one aspect. So the shape also matters, like what kind of so a lot of things are there. So one aspect is this anti-reflection coating. So you can hide the signature of the your aircraft by many other different means, but this is one of the way. Is it clear?
Yes, sir.
Yeah.
Thank you.
So basically, you will optimize the material, that the coating that you want to put on the aircraft surface. So you also have to make sure it is lighter. So you don't want that the weight increases too much, because that will compromise on the speed, okay, on the performance. So there are many parameters need to play with. This is one of the parameters. Okay. Yes. Okay. So if no more questions, so then thank you. So we'll meet then in the next class.
Thank you, sir.
Thank you, sir.